just to be a little bit familiar with Snap. So okay, so we go to the data. So I hope that you have done a similar folder with me, like the folder file snap to stamp. You got that folder?
Yes.
Yes.
Okay, so suppose that we have that folder. So we go into this one. We go into click on master, and you see there is one image here, right? You got in zip file. So we just try to do try to explore Snap using this image. So whenever we have this image, so look at carefully and slowly. I select this one, I click on this one, I move, and I drop it here. You see, drop it here. Then it's done. So it should be open the image for me, but okay, it takes some time. You see here, it's done. Everybody follow. So everyone follow me.
Yes.
Okay, because it's quite basic and very easy. So I just want to repeat very slowly for you. So I have the snap, I have the folder. So I click this one. I click and I drop it here. Okay, so okay, whenever I drop it here, I click on the plus icon here, and you see there's some information like metadata and the information of the image. So for example, metadata, you can click on this one. So abstract metadata. So in this one, you can see there's a table. We will show you some information like, okay, so what do we have with the data here? So some parameter important is in the size of the pixel. So you repeat it here. The image in radar, we have a 2 dimension. The first is in random direction. The second is azimuth direction. So basically with the Sentinel-1 data, we have something like in rand is 2.3 meter. For the azimuth direction, we had about something like 40 meter. Okay, so that is the size. Okay, so we have some information like the center of latitude, like this one. That is just some meta information to understand it. And then we got to open this image. So you click on the band and you see there is some information. Like we have the first, the ISWAT 1, the ISWAT 2, and the ISWAT 3. Why we have a 3 SWAT here? Because remember, this one in the Sentinel-1 topmost, they do when here they do SWAT 1, they change in the pointing up antenna angle, and they do collection with the SWAT 2, and they do it the same for SWAT 3. So with Sentinel-1 data, with the top we have 1, 2, 3 SWAT. So you know where it's come from. Okay, and you see here when they take this one and they move a little bit here, and they move a little bit here. So each one we call it a burst. A burst. Okay, so this one. So this one will be overlay a little bit on the second one, right? You see, the first will be overlay a little bit to the second one. You see, it's very clear information here in the snap. So suppose that I go to this one and so, okay, we have a 3 SWAT here, but I don't want to open it now because I don't want to see information not really necessary for me because it can take some time. I just want to exploit all the function. Like, okay, I click on navigation. I don't know where it is. Color it, no, I send it work field. So we see here. click on this one. So just to appreciate where we are. So that is the image we have. You see, this is the coverage of the image. So the footprint of our image in here. Some is related. You can find it in Mexico City. And then some useful menu which we can be appreciated like file, edit, analysis. Like in analysis, we have some function, and then we go into radar. That is our main menu to working on. So support we have to apply office to correct our orbit data, and we do something like radiometrics, filtering, or correlation, in interferometry, polarimetry, and so on. So we done in the radar menu here. So suppose that I can moving on a little bit, go into the system. Got this one. So, okay, we're moving on. The next system should be top. So I hope you have this this document. I'm going to show you how to do. So our goal is to try to able to generate this subsidal map. So it's quite a little bit long. So if you cannot follow my instruction, you can read in your, you can check it again in your document, and to try to repeat it here is quite easy. So basically that's the image first, the open image, okay, and then we're moving on. Okay, so that's our material. Okay, so first, second. So that is the first, and in Snap, everything we can select this one. For example, we can apply a bit, right? Whenever they have a window like this one, that we always ask you where is the data for the input, and then where is the processing parameter, and then you can have to tell them where to store the data. So everything you can done it repeatedly by window here. Like everything you open, they can ask you some information, but the most important information is the input one here. So you can do it step by step using the menu like this one, but it's not really efficient. So the one way more efficient, more powerful in Snap is they offer the graph builder. You see here, you can move into the graph builder here. You click on graph builder, like this one here. If you want to do some certain operator, you can right click on your mouse. You right click on your mouse. You can add a certain application, like okay, like we go to check apply object. Okay, suppose if we want just to do apply object, we'll click on this one. Click on this one, we link together. You follow? No. So yes. I delete it again. So to try to be sure everybody follow, so I click on the graph builder. This one. In here, if we want to add something, we right your mouse and we add information here. So in radar, we can add the apply orbit. You can add some maybe the radar. You can add into Sentinel-1 data, you can add maybe just slip information like this one. So whenever we have the operator like this one, and we want to link it together, so you move your mouse here and you put it here, and you rub your mouse and it links. The other one is the same. Okay, is it easy for you? Okay, so now we got just try to a little bit got a little bit familiar. So, but now in your tutorial, I already gave you this one. So, do you have this folder?
Yes.
Okay, so so pay attention with the slip and apply a bit. So I got to lost this one. So in IGARSS 2021, we going to folder 4. I click on slip and apply a bit. Okay. Right? And you see this one. I'm sure you got this one. I go very slowly here because everything will be the same after that. Okay, so we have the data input. Okay, so we have this one is the input data stop slip. What about the tutorial? In our tutorial, we should be in IGARSS 3 and in burst 3 and 4. So we select the IGARSS 3 and the burst 3 and 4 here, right? Okay, so slip IGARSS 3 and the burst 3 and 4 here, right? And apply all this, and then we want to be sure everything is done. We be generate a file, so we have to add the file. So you write, you add it, input, and you write. Okay, and then you have to link it together. So you move your mouse here, you click on this one, you put it together, right? Okay, and then in writing we okay, so where I want to put it, oh, it's the same folder, so I want to have this name. Okay, so everything done? Question? Sorry, why we not run anything? We still not run anything. Okay, so just want to ask you that do you have the same problem with David? That I mean, the snap respond very slowly. I mean, whenever snap is slowly, just try to turn it up and open it because maybe the Java they not really good in memory management. So okay, so I just hit the run and to see is this slow. So everybody follow. I hit the run. Okay. So the question is it important to select the VV polarization? Yes, it's important because it should be the same polarization for every image to processing, and for interferometric application, the cobalt like the IGARSS and the VV is more accuracy rather than the crossband ASV or VS, because the ASV and VS is referable for some volumetric application, some volumetric scattering like in forest or like in rice or in array catcher scenario. In that case, the crossband is really good, but for the application in the motion, cobalt is good, is better. Okay?
Excuse me.
Yes.
Can you show me, please, the variables of top SAR split? Which boards is? Can you repeat, please?
Okay, so in the top,
so IBW 3 and 3 to 4.
3 and 3 to 4.
Thank you. Thank you.
Yeah. Just want to mention with you that if you lost something, that you have the documents, and in the document I very well record everything. Okay, so everything is okay in the document. So not so bad. David, in my computer it just takes 16 seconds. Not so bad. So we had the first image. Okay. Okay. So we keep going. Okay. So we track it, this one. So now compared to the first image, we have just SWAT tree, and you can open the image by double click on this one. And then they will open the image for you. So in that case, you can move it on here. You can click on navigator, navigation here. You can click on this one to appreciate, to zoom. So you can bend it here to see the image. Okay. So you see here, we select two bursts, burst 3 and 4, and you see between burst 3 and 4 here, there is some information overlay, but they record in different matrices, in different positions, to be sure that the system know where in the burst 3 and where in the burst 4. So you see here, there's a gap here. So after we do processing, we will remove the gap later. But you see in the raw image, the gap should be something like this one. So basically what we've done, we just try to apply the orbit to update information of the orbit information. And then we just try to extract the image to the area of where we are really focused, right? We don't need to work in the whole image. So you see here, that is the whole image we have. We select just a small area here where we are interested on, right? Okay, so we do the same for the second one. So we got back to the tutorial. So the tutorial, we are here. So we are here. So we go on to the second one. So the second one should be the image of 2009, and we have to select the burst 8 and 9. So to be sure that everything is correctly the same area. So we go into the second one. We go into this image. So to be sure everybody follow me, can you check in your computer, do you have the same folder with me?
Yep.
Okay, so we select the one in 2019. We click and we drop it in the snap, right? And then we do the same for sleep. Oh, we forgot to say, don't worry, we right here, so we link together here. So it should be right. So in the second one, we select the number 3 here, so it should be 2019. And sleep, we go into sleep tree as SWAT tree. We select the cobalt VV, and this one, it should be in the burst, should be in 8 and 9. So you move it here. So you move this one slide 8 and 9. Okay, so you got it. Everybody follow? So you move A and I here, and you apply all this, you keep it the same, you're writing. So you put this one you put in the format circle, right? And okay, so I put this one in here, 2009. Okay, so everything's okay. I hit the run. Just one question. Is the order between slip and apply all this important? In my opinion, it's not important. Because why? Because slip and apply it is the same thing, because they not done anything. They just extract information. They're not done anything in terms of analysis. So there is no problem. Okay, so we have 2 images now. So to try to be sure that is the first image and the second image is here. So you see that is the second image, and the first image here, the second image here. So everything is quite look like similar. So it means that the same area is extracted from 2 images. So the first and the second. Okay, first and second is done. How do we identify corresponding bursts in the master and slaver? By just by viewing, by tracking. Because why? Because at the beginning, like the master, we want to focus in which area. We had to open the whole image like this one. We had to open the whole image, and then we try to just wait a moment, because when we open the whole image, it will be, it takes some time. Okay, so we got the image here. So you see here is the whole image for the first one. So can we calculate can we count the number of frames together? The number of bursts, sorry. So this one is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, usually one image is about 9 or 10 bursts, and I know very well that 1, 2, 3. I know very well that our area of interest is in burst 3 and 4. So the first image, I have to open the whole image to know where exactly it is, and then I try to extract it. That is for the master. And for slaver, we do the same. Where is slaver? Okay, for slaver, you see here in the second image, we can count together with me 1, 2, 3, 4, 5, 6, 7, 8, and 9. 8 and 9 here is corresponding to 3 and 4 here. So 1, 2, 3, and 4. Here is 8 and 9. So basically that we have to open the image and to track it. Time consuming.
I have a question. Excuse me.
Right. It's time consuming, but okay. Gianluca, right? How can I spell your name correctly?
Yes.
Gianluca. But don't worry, he just a very beginning, so I just show you how to handle from the beginning. But after that, we had a tool to do automatically, so don't worry.
Okay.
But at the moment, I just show you how to handle it at just by looking at to see where it is. But after that, we have the toolbox to do it automatically, so don't worry.
Okay. Thank you very much.
Welcome. So where we are now, everyone. So we have the first and the second already. So 2 images already. So what we're going to do is to do correlation. Okay, so we do correlation. So we're going to correlations, we're going to gap, and we got to load this one. And in the folder, we have the correlation interferogram. We click on this one. Okay, so we got this one, and this one it don't have the written there, so we have to write here. So everybody follow me. I open this one, and I got this one. So basically, that's they add something wrong. They add something here. They add that the slip for that should be expected. So we don't have. Just try. What exactly it is? Okay, so we have to add right it first. So we put it here to link together, and we put it here to link together. So like this way, we have exactly the same gap in the tutorial, right? And then we move into the some parameter input, like the first. It should be the first image, like this one, and the second one should be second one. Okay, right? So there is no message here. So I just so back projection. I click on this one, so everything is okay. From everything's okay. I let it. This one everything's okay. I just let it there. Interferogram. So I click on subtract. So 15 and 3. Okay. So this one. Okay. So right in here, so we got this one is interferogram. So this one is correct. So it's 5. Yes.
Can you show me, sorry, again, the read and read 2? Read is the master and read 2 is the slave?
The first one is in 2018.
Mm-hmm.
2019.
Okay. The other steps are just by default, right? Or
yes, yeah. The other step is let it default.
Right. Thank you.
Yeah. To be sure that you should have this one. Yeah, like this one. To be sure that we have the some information right.
Okay.
Okay.
Thank you.
just want to repeat that if you lost, you have the document here, right? To be sure that. So I hit the run and I expect that we have got something done after a few minutes. Okay. So basically, that's the decoration. It takes some time, about a few minutes, I guess so. And meanwhile, if you have any questions, feel free to ask me.
Yeah, I have one question. Is it usually must be the same orbit, right? It must be the same orbit, the two products.
What you mean to orbit? It means the same track. That's what you mean, right?
Right, right.
Yeah, it should be the same track.
Yeah, thank you.
The same relative orbit number in the Sentinel-1 data, Sentinel-1 data, or whatever the satellite. When we do the coherent analysis like interferometry, it should have the same orbit. Kind of say the first and the second, the position of the satellite should be quite close together.
Okay, thank you.
We cannot cross orbit, because cross orbit we don't have the phase information. Yes, David, please.
In the interferogram tab, you remove the flat Earth. Why don't you remove the topography?
We move topography also.
Okay.
Yeah, we have a topography step here.
Okay, okay.
We have to move. We have to remove it, of course.
Do you mind going back in the interferogram?
Yes.
You see the subtract topographic phase?
Yes, it have, but because sometimes they don't have all the full option like this one.
Okay.
Because if we want to do something like G-coding later, we need to have the longitude and latitude then. And this one is sometimes they're not really, I'm not sure. Yeah, they have it also. But I mean, because when I do this one, it's just how can I say? It just used to be like this one. So but it's the same thing, I guess so.
Okay.
If we remove this one and in the program we can click on this one and it will be the same, I guess so. But here just because why I want to decompose it, because to have you understand when we do the interferogram we have to do topography removal on. So basically that we have to calculate the topography contribution and remove it. So for people to maybe more easy to understand between the theory and the practical.
Okay.
Okay, perfect. Feel free to ask me, David. Whenever it's done, you will see some interferogram like this one. I expect. So David asked me that I still get stuck at the first step. Connect to the Sentinel-1 bit fail. Cannot select. Sorry, is there anyone who got the similar error like David? No. David, my suggestion is it the newest version of Sentinel-1 data of the snap?
I use the version 8.
Version 8, and do you make something like update? I mean, you go to here and you check for updates like this one.
Yeah.
Yes.
Check for that. Yes.
Yes. The bus should be done before correction? No. Because why? Because the debuggers they need the information of the master, and they use the phase information from the master, then they subtract it for the master and for all the slaver the same thing. So basically that they need to done the correction before to have something consistently. So we have to done correction before the debug. Because why? Because basically that's when we do the debug, basically that they we don't have anything with the bus one and bus two. We don't see the black one area. I mean, they will remove that one when we do the debug. And when we do the debug, we remove the information of the interferogram in that area overlay. And without the interferogram overlay in that one, we cannot have the spectral diversity. Spectral diversity, it means that's the double interferogram of the interferogram. So that's what we call the spectral diversity. So I mean, when we do the debug, we don't have the information for the spectral diversity. And without that, we cannot do correlation. So that's why we cannot do the debug before correlation. To summarize, that during the correlation, the data should not be debugged. Back up.
Excuse me, can you explain again, please, about the enhanced spectral diversity option?
It has spectral diversity option.
Yes, please.
Yeah. So basically, that's because batch coding. What does it mean here? That's the first image and the second image. When they do batch coding, I mean, they just try to build a lookup table between the radar coordination system and the last long coordinate system using a digital elevation model that we call batch coding. And with that information, we have a tomography information during correlation. I mean, this one is just trying to have us to have an elevation model, I mean, tomography information during the correlation. And during the correlation, when we try to do correlation, they have 2 dimensions. The first is in slant direction, and the second is in azimuth direction. In slant direction, is basically that's what we can done easily using just classic technique like in strip map. But in the azimuth direction, where we had the burst continuously. So for the burst in the azimuth, they require the correlation very high accuracy, something like 1.5 centimeter accuracy. It is difficult to achieve this requirement without a certain technique. So one way people achieve this accuracy is they try to do the interferogram For the burst one, I suppose, okay, maybe I wrong, maybe one here for easy to understand. So we are waiting, so don't worry. So we have time. So suppose that's one in the first. Okay. Okay, so that is the first image and the second image here. So the image one here. So the image one here. So that is the image. So like we have the image one here. The image two here, right? So we have the image one with two bursts like 3 and 4, image two like 8 and 9 here. So we have two bursts corresponding. So what we do, what the people do to get achieve up something like 1.5 centimeter accuracy correlation. So they try to calculate the interferogram of this one and this one. So I suppose that is the best one. Best one. The best two here. So this direction is slant rand and this direction is azimuth. So they want to calculate spectral diversity. It means that they take the first and the second here. So for the first one here, they got something like, okay, so they overlay this one here. Suppose this one. No, I just wait. So E1 and E2 here. So it means we have to take so we multiply with conjugation. So this one we have the interferogram of this one by this one. So we have the interferogram. So here is the bus one and here the bus two also, right? And then because the bus here one here is usually they have something like overlay.
Yes.
Something like overlay here. I mean the bus one and bus two should overlay something here. How can I just put it here to be sure that there's no image? Okay, like this one. You see here, it's an overlay here.
Yes.
So the overlay here, they calculate for the bus one. They calculate the phase difference for the bus one and the bus two of the interferogram here. So basically that's the bus one, they multiply the conjugation of the bus two. But just for the overlay interferogram here. So basically this one, what we say the double interferogram. Because the B1 here is, so let me say EB here for easy, right? So, and EB1 is EB1 is for this one.
Within the same burst.
Yeah, EB1 is here.
Yes, yes.
You so EB1 is here, and EB2 is here. So basically, that is the first image and the second image. We put it together, we subtract it, we got the interferogram, so we got EB1, IB1, right? And the second, for the burst 2, we do the same, the burst 1, the burst 1, and the burst 2 here. Just my computer cannot see. So we take this one, we subtracted one, we get the IB2 here. So IB1 and IB2 is actually the interferogram. And we take the overlay where the burst overlay a little bit here. We take the subtract this one and this one, basically this one multiply by conjugation of this one. So we have a double interferogram. So, and this one we call it the spectral diversity. And from the interferogram, like this one, so basically that's just the phase and they corresponding to a certain displacement between this one here. So basically in this area here, we try to select the good position, and they extract the phase and they extract the certain changing, I mean the certain offset here, and then they calculate the offset for the first and the second, and then they just try to correct that offset, and that's done. So that's that we call the idea of spectral diversity. So basically that they just try to do interferogram of the interferogram. And that's all. And in that case, people can get an amazing accuracy like 1.5 centimeter. So the one question is, can I choose subtract tomography directly from? Yes, it's the same thing. So who asked the question already? Thomas, right? Now who asked the same question like subtract tomography directly interferogram step? Yes, we can do it. It will be the same. I mean, people ask in the interferogram, we have the subtract tomography phase here. We can do it here. Then we remove this one. Why I put it here? Because I just want to decompose it here to maybe more easy to understand. Okay, but it will be the same. Or just want to be sure that everything done for you, because I'm done. So I have interferogram. But just because people have highlight a lot in subtract tomography phase during the interferogram step. So my response is it's not really different, but when we go into a little bit detail, it can be have some minor effect if we do some something unnecessary before the burst, because after the burst it will be easy to get how can I say I had to lost this one again just to be sure that we discuss the right one here. So the question is, in the interferogram step, we have subtract tomography phase, and is this good or not good to do it before the burst or after the burst? So in my implementation, I recommend it to put after the burst, but even that we can do it before the burst. I mean, I guess there is nothing different, because there is no mathematical related between the reverse for the tomography phase removal here. So in my perspective, it's the same, but I'm not sure in SNAP it will be the same, because in the theory it will be the same, but in SNAP I never checked it before. So pay attention if you click on this one when you're done in your application. But in my tutorial, I put it here as a usual way, because I be sure that everything is correctly like this one. But theoretically, it will be the same if we remove the tomography phase before the reverse. So, but in the SNAP, I'm not sure because when we do implementation, there is some requirement constraint. I'm not sure for SNAP. I'm not sure. Okay, so we got the phase. I open the phase. Okay, so we got something useful information. So you see here. So we got the phase is not random. Here is the phase random, right? Because that is the area where a lot of vegetation, so that's called random. So if we go to here, we got something phase information, right? Okay, so we got the phase, but it looks a little bit noisy. So we want to improve the quality by a certain technique, like the one we show here is the multi-looking. So basically we got to radar, we got to SAR utility, we got to multi-looking, and then we go to try. Okay, so we want to SAR utility multi-looking. So the data input interferogram, so Mexico, so the parameter, so we put it here. So we want to visualize this one, we want 15 and we want 3. It's the same in tutorial. So okay, the same tutorials, I hit the run. So 3 seconds. So it's very fast. So just close it here and to drag it here. So to drag to the face. So you see here, the face is more clear now with respect to the original one. So when we're done multi-looking, we can see the face like this one. And we can even, yes?
Sorry to interrupt. Is there a specific reason why we should put independent looks 15 and 3? By default, it's square pixel, and I think my computer it says 4 in range look, and azimuth looks is 1.
Yeah, it's just a kind of say when we done multi-looking like this one, they require some parameter like independent or square pixel. That's people estimate to be sure that the dimension of the pixel should be the same for the azimuth direction or in random direction. Yeah, because when we select the 15 and the 3 here, it depends on the pixel size. We remember it in this one. You remember that we got this one, so we got a track here. So we got something like where we are. So the attract attribute looking. So we got information. So we go to interferogram. We select the attract information. We will see the pixel size here. So basically that the range spacing is about 2.3, and this one is about 14. So we got something like okay, like something like okay, 2.3. We multiply by something like 15 is about 34 meters, right? And the azimuth direction we have something like 14. We multiply by 3, so the 42 meter. So basically here it is approximation, right?
Okay, thank you very much.
Because we just want to be sure that the dimension between the two directions is not really totally different, right? Like, okay, one dimension is 213 meter, and the other dimension is 40 meter. It's quite different. So I want to give some number of look exploit, because in the range direction we have many independent looks, but in azimuth direction we don't have many. Like this one, if we have in azimuth direction, we got something like 15. We multiply by 14, if we end up with the dimension of 210 meter, and the other one is just about 213. Then we multiply by 3. It don't make sense. So to try to get something quite closely, something reasonable. And for my application, usually I put 3.15 or 3.20, yeah, to try to get something quite reasonable. Oh, where is this? Just open image. Yeah, welcome. To track image. So I open the image here. So you see, let's track the information here in the metadata. So when we done the multi-looking, we will see that the range spacing is here. You see, one direction is about 35 meter, and other direction is about 41. So it's quite similar. So it's quite not really different with respect to the original one. So that is the idea from the idea to give the number up look when we done calculation. Okay, so where we are when we done the multi-looking, we got the quality is quite nice, but we can even improve it by using one more technique, using the filter. So we got to a certain filtering. We using the constant phase filtering. So we click on this one. So where we are, just try to be sure that everybody cuts it up. Okay, so we done it here. It's looking, and we're going to filtering. So we're going to constant. Okay, so we done it. So let's track. So keep everything the same. So run it. So we got a filter. So here you got the version of before and this one. So you see there's some improvement. Like this one is before filtering, and this one is after filtering. So you see there is some enhancement. So whenever we have the good one, we can see some information like, okay, here we have a coherent. We can click on coherent. So you can see the coherent is something like just dark and white. So just the other one is just between the black and white. So you see this one is totally dark. So we expect that the relation between the first and the second is very low. So the noise should be totally random here. So to be sure that everything is correct as I expected, here is coherent, and we track the phase. So we see here, totally random here, right? And then here the phase here is very clear. So I get the coherent is very high here. So I expect that the phase, wow, you see the phase here, very clean. A little bit noise here because of the coherent is not really good here. So and so on. So where we are now, when we done the filtering, what we are going to do, we do phase unwrapping. So to try to remit why we had to do phase unwrapping, because the phase we have is just ranging from -pi to +pi, just to be sure that that's the phase, its color scale. You see here, in the navigation, you click on the color scale, you see the value is ranging just about minus pi to plus pi here. So the phase is always wrapped in that limit. So if we want to have the absolute phase, we have to do phase wrapping. So how can we do that? We have to be sure that we're going to export going to unwrapping. We have to use all the toolkit because it's not implemented in the snap. They have to use the snapful toolkit. So we go to radar. So it's quite a little bit tricky when we do phase wrapping. So I'm going very slowly for you to be sure that everybody can be just going to interferometry, going to unwrapping, going to snapful export. Everybody follow? Click on that one. So the one we want to export is, of course, the last one. So the multi-looking and featuring and snap export. So what we want to go where? So so basically that it should be in the direction. Okay, so we will snaffle. Okay, so the importantly we will have to put it in a deformation. Everybody pay attention, please, because when we done it here, we had to be sure that everything is smooth. We had to put this one equal one. Otherwise, we had bath problem. Okay, one, please. It's important because I'm already highlighting the documents. So we have one. Is okay for everyone?
Can you say what is the reason why we selected 1-1 instead of 10-10?
Because for example, the image, if they have very big, so they divide the number of processing by many path image. So like divide, if they begin 2 by 2 here, so they divide the image as for the image like this one. So they divide image by 2 and 2. Let's process this one, and this one. So in that case, we end up with the rate of the not really smooth between the paths, because we can have the path, they're not really continuously. So it's better to put just one here, to be sure that everything is globally, not locally. You got it? And then the other one is just okay if you have your computer processor or cost-free host, just put it the same here. So hit the run. So try to repeat it. 1 and 1 is important to be sure everything consistent. Okay, hit the run.
Okay, thanks.
Okay, so done. So whenever we done it, we're going to interfere, we're going to unwrap it. Try to repeat again. Radar, interferometry, unwrapping, snafu unwrapping. So that is the one where it's super us. This is the one we export it here. Where we are, when we it should be here. So we have snafu, well, this one. So you see here, there's some file that's export here. So what you're going to show is you select this one. So I select that one. So snafu. and I select this one. It's okay, everyone. I select this one. Okay.
Excuse me, I think
Yes.
I'm a bit behind. I just finished export to Snafu.
Yes.
Can you repeat, please, after that?
Okay.
I'm sorry.
Have you done the export? Yeah. Can you find the folder here?
Yes. Yes.
Okay.
Yes.
Okay. And then to just go into radar. You go into interferometric. You go into unwrapping. You go into Snafu unwrapping. You click on that one, right?
Okay.
Okay. So we're going to show you. We have to select this one, the phase interferogram, and we have the extension after as the R.
STR. Okay.
So basically, that's we're going to this one to select this one. Okay, you follow?
Yes. Yes.
And then we're going to process parameter. We click on this one. So output folder, it should be exactly the same folder here. So I just copy and validate here. So done. So to try to repeat with you, that's our folder. We have to put it as folder. So I to be sure I copy. And then I hit the run. We're going to run it. So it will take a couple of times so we can enjoy it to ask question. So Emmanuel, sorry for the very first question. Emmanuel asked me, can we record this tutorial? Aha, good question. I just want to check that. Can I share your security to record this for this? Authorize. Emmanuel, are you there?
Yes, I'm here.
I just checked the security of the IGARSS. You see here. So basically, that even I want to let you allow to record the tutorial, but I cannot find where we select it. If you know.
Let me try. It says here that I need to ask you for permission when I click on the.
You need to ask me, huh? Let me track. How can I do it here? So, up to now, this one. Up to now, which one is the most sensitive parameter in the processing flow? Workflow. Let's say the most sensitivity is how can I say the orbit. Without the orbit, everything can be failed. That is the orbit information. And the second one is because we are dealing with the phase unwrapping, we need the phase very high accuracy and no noise. So maybe the multi-look is also the very important. I mean this one here. So this one is also very important. There's the multi-look until now, but just the more important is this one. In the apply orbit, if you don't have the good orbit, everything fail. It's not sensitive, it just fail, and it just cannot be done. So the sensitivity and the orbit is very important. So in case of without orbit, it's really difficult to do with the top. Of course, with the strip map is something easy, because with the top, we don't have the orbit information with the high accuracy enough. We cannot achieve. We cannot achieve this one. Where is this? We cannot achieve this one. Without the orbit accuracy, we cannot achieve this one. And without correlation, we cannot done anything. And after that, for all the parameters in the interferogram, I think maybe the multi-looking, I mean, the way we improve the interferogram is very important. If the multi-looking is bigger, and then it's going to smoother, and it can be good for you, but also we pay for the resolution, because if you using many multi-looking, so suppose that instead of let's try.
Excuse me.
Yes.
I get an error when I was trying to apply the snafu unwrapping. I don't know if you're familiar. Can you help me? The message is variable snafu tool x is not set, and also snafu.x is not set.
Yes, maybe that's the problem of not automatically that. Let me check that. Whenever you done it and it's not available, you can go to the folder. And this one, you see the folder here?
Yes.
You see the snafu configuration. Did you see that?
Yep. Yes.
And you can maybe just at this one. You see, if you cannot run it directly in the snafu, you can run it in terminal, like this one.
Oh, right. Okay.
Okay, let me check how can I run the terminal together with you. Okay, like this one. Okay, so where we are now. So okay, let's suppose that I have a configuration here, and I have a snafu line like this one. So I just put snafu and I'll run this one here. Something like this one.
Right. So I just run this in command line.
Yeah, in going to the command line. You using Linux or Windows?
Linux. I have a Mac.
Okay, so Linux, you just write the stuff and run it in the terminal, and it's okay. But it should be in the folder of where we have the data, right?
Okay. I'll try. Thank you.
Welcome. Okay, my one is done. Okay, so it takes something like 4 minutes. So whenever it's done, I close it here. So discussion. The signature noise affect different effects of frame wrapping. Yes, of course. Therefore, it is necessary to perform 2-step of multi-looking and fitting to review noise. Yes, of course. Because whenever the signal to noise is really low for the phase, like this one here, like you see, like this one here. You see here, is very noisy, and when we do phase unwrapping, it's difficult to understand where we need to add up a certain number of integer. I mean the number of frequency, number of 2 pi to add to during the phase unwrapping. It's difficult. Rather than we improve the quality of the interferogram like multi-looking. So between this one and this one, of course, this one is much be more easier to do phase unwrapping. So it's strongly necessary to be summarized. To be very clear, it's very, very important to enhance the quality of interferogram before doing phase unwrapping. So my one is done. So what do we got? So after I'm done, I got this one. So I got a fine wrapping here. So after a couple of minutes, something like 4 minutes, I got this one. Okay. Whenever I got this one, okay, what is this? Okay. Okay, so we got this one here. But and then I just want to input it in. So how can I? So okay. So after I'm done phase unwrapping export, I want to import it here. So I have to go into phase unwrapping. I got this one for input, and I got this one for that's it done. So we're done for phase unwrapping, and then we're going to import it into here. So we're going to import. So we got this one. So it should be the multi-looking and filtering, and then we go into select for the header. And we got into wrapping. Okay, so we got it here. So basically that we go to radar, go to interferometric, go to final wrapping, we have to import. Just before I'm doing this one, everything is okay for you. Are you done it also? Have you done it?
I'm running in the command line, so I must wait a little bit. I think
it's 4 minutes.
Okay. Okay, I think it's running. Thank you.
Okay, it's running. It's fine. So it should take 4 minutes. So because this step is quite a little bit not easy to for everyone, so it's better to wait a little bit so everybody can follow me.
Thank you. Thank you.
Welcome. The objective is everybody can do something, not just listen. That's the objective. So it shows it's showing starting to accusing 100% stop there. It's not done. Did you check you have this one?
Yeah, it finished. I think I got it. Got it. I'm ready.
Okay. So you ready to import everyone? Can you give me another voice, please?
Yes, for me.
Okay, great. So we can do together. How can we import? So we're going to radar, interferometry, wrappings, import. So first we have to select the right one. So it should be this one. That is the sub products we are going to edit here. So the second one is unwrapping phase. So where is it? It should be the one so here we should select the one have the extension header. So it should be click on that one. Okay.
Excuse me, can you show me the first one? Read face. Which file should be?
It should be the one we do filtering.
Oh, right. Okay.
Okay. The one we do multi-looking and filtering, and then the one here should be the header. And
right.
then
Thank you.
Is we keep and can keep it here. So the final one it should be here. So where is this? Web folder. So I put this one, it should be in unwrapping. So I hit the run. So what do we have? We have the one here. The first is the unwrapping here. You see?
Yes.
Okay. So I just give you a little bit, 1 or 2 minutes to import it correctly. So we have the unwrap phase here. And then jump in tutorial so to know exactly where we are. So you know, so we have it here. So we have the unwrapping, and
I'm sorry, can I have one more question?
yes.
When I'm doing the import in the option right, should I change the name because it's the same name as the one read phase?
We write a new name like unwrapping here. See?
Okay, sorry, thank you.
So everybody can appreciate the information we see here. So basically the phase here is corresponding to much larger than the scale of minus pi to plus pi. So basically that's vary from minus 4.41 until something like 37.55. So you see, we got the absolutely phase here. So what can we do now? What can we do next? So our other step is to try to do the phase to displacement. So we want to convert the phase information to the displacement. So basically that it should be it should convert by this one. So we have the phase here now, and then we want to convert it in displacement. So basically that they will change in with this one. So basically they will take the phase, they multiply by the wave and by the wavelength, and then divide by 4 pi, and you got the displacement. So very easy for snap. So we on to radar. Where we are, we on to interferometry, we on to border. So we on to phase to displacement. We click on that one. Okay. Okay, and then to try to be sure that there's no requirement for parameters. So be sure that should be the unwrap one. And we run it. So I hope it's done carefully. So we got displacement here. Here the phase and here displacement. So what is that displacement? They vary from about something like 0, I mean stable, until something like minus 0.17 meter. Remember, here it's a meter. So basically that's can we do something more beautiful? So where we are, so we got affected to displacement here. And okay, so you see in my tutorial, we got a very beautiful color, and we got a profile to appreciate the information. When we see here is stable, when we see the parameter, the subsidence is going down a little bit here, and go back. So can we generate this figure also? So basically that, so you have the color, you go to color pattern, you select this one, you just one, so you click on that one. Is the right one? No. Look at the right one. Yes, excuse me. Yeah, this is vertical displacement in a left side. It should be left side. This one in line of sight, please. They just simply changing the phase. They have the phase and they're changing into the distance. Just simply the phase and the distance. So there's nothing with the vertical displacement here. So okay. Basically, that's whenever we have just one measurement. It's usually it's better to keep it in line of sight direction rather than vertical direction. Because why? Because it's better to use all the measurement to complement to convert it to vertical displacement. Something like if we have ascending and descending together, we join together, and we have the vertical and the horizontal west and east direction also. It's better. If we have just one measurement, usually it's just better to keep it in line of sight. So now we have this one. So what do we have? So we can appreciate this one is very that is a very risky area here. So we want to be sure that everything is okay by the track. It should be stable here, should be stable here. And we want to have a profile for this one. So you can click on this one, click on this one. So if you want to generate a profile, just click on this one. You see, everybody follow me, please. So you have my pointer. I click on this one. So line drawing tools. So I click this one. I click this one. So okay, I got this one. Okay. And then I want to see the profile or the cross section along this line. I go to layer, I'm going to analysis, sorry, and I see the profile plot. You see this information?
Yes.
Okay, I click on this one. So basically that's because I use this one. So I click this one and whoop, it doesn't, it's not recognized. So what is this? I got it here, I click on this one, I go to analysis, I go to profile. Okay, sometimes it's not really synchronized, so we have to track it here. So to try to repeat for everyone to follow. Okay, so I click on this one, I draw one line, this one, and I go to analysis and go to profile plot. And you see here, so it's not exactly the same one. Why? It's not synchronized. So about analysis. Okay, so sometimes we have to click on this one to synchronize. So you see here, when my pointer is here, the area is quite stable. But when we go this one, so it's going down a little bit here. We go down until something like minus 2.5 meter. So basically, that's the data we have in 2018 and 2019. So 1 year almost. So 365 days, and we have something displacement, something like 25 centimeter. You see? So okay. So what they're the set? What they're the setting? The Sentinel is profile constant. This one. You mean this one? This one is just pointing the position where we are on the image. So you see that in the center where we have reception a lot. So this is just a pointer of the profile.
Yeah, there is some shading behind the blue line.
Ah, some shading behind blue line. Where is it? I cannot see it. Let me check. You mean this one, right?
Yes, yes.
Yes. This one is can be understand that because when we calculate there is some not only the line here, but they calculate some bond nearby here. I mean some neighborhood, and they show you the ranging of the value here. So basically here they're not taking into account just one line, but I mean they buffer a little bit about maybe 10 meter here. I'm not sure how to understand it because my computer is a little bit difficult to zoom it here. And you see some shape here. Just show there's some variation because the profiles they're not necessarily just one line, but there's a buffer. So they at one position there's some not only one value but some value here, and they calculate for something related to standard deviation, and they plot in a shapefile here just for visualization. So just wrap your mouse and jump on the session. Okay. I remove this one. And paste this one. Okay. And I click on profile again. Okay. So just wrap your mouse and jump on the session. Okay, you got it. Okay. Okay, you see. So basically, here it's just a buffer, not only one line. So at one position, they not just only one value, but they take into account some bond nearby, and they just show you the idea of the distribution of the profile or of the cross section. Just something for the distribution. So you click on this one. So thank you a lot for David. So you see here. So it's interesting. So now is this enough? We're not finished because why? Because we know that the coherence is sure that the coherence is good quality. Where we are for the coherence. Like this one. But you see, the coherence is the only indicator to tell us the quality of the interferogram on the phase. Usually, if the coherence is close to 1, it's pretty good, and it's close to 0, it's just noisy. So basically, that is set to remove this one. So usually in application, that if the coherence lower than 0.2, that should be totally discussed during further processing. So in our application, we try to mask out the area where we know that the quality is not good. We suppose that we're using the coherence about 0.5. Less than 0.5, we not consider it, and we try to generate a mask, and then we apply a mask to our final product. So how can we generate it? So we got the phase and the coherence here. So we want to estimate the mass. So basically we click on this one. So we go to here, we click this. So just pay attention here. We right your mouse. We select this one. And we just write something like, okay, mass 0.5. And here we try to do some threshold by edit one. So we click on this one, edit expression. We select the coherence where it is, should be one here. And we should be greater than 0.5. And it's done. It's okay for everyone. So whenever it's done, I click on it's okay. So we have the mass here, you see? Here's coherent and here the mass. So basically, whenever the coherent is lower than 0.5, we put it in 0, and otherwise it should be 1 in the mask. So we take the mask, we multiply by the displacement we have here. So we take the mask and we, so where we are, we take the mask, we have the mask, and then we take the mask, we multiply with the displacement. And then we got the displacement final. So where we are, so we take this one, the mask, and we multiply. So it should be displacement final. So we got this one. So it should be where the mass, no, mass, and we multiply by displacement. So where displacement should be here. So it's very easy. So you take the mass and you multiply by displacement. So the idea is just try to not consider the area we know the quality of the phase is not good. So we, okay. Okay. So we change its color. So the blue one should be close to 0, so it's not necessary to see it, so we put it in a non-color. So we got this one, right? Everybody follow?
Yes.
Okay, great. And then we try to, how can I say, have a better communication with other people, try to export it into Google Earth, for example. How can we do that? We just try to do G-coding. How can we do that? We just try to go into rand doublet terrain correction, and then it's done. Just try radar. It's okay. So we're going to radar. We're going to geometry. We're going to terrain correction. We're going to rand doublet terrain corrections. With that one. And it's okay for produce parameter. So the one we just want the displacement final. So we want to have the output of the pixel is something like 50 meters. So okay. So it's running. So what do we have? So we have it again here. So the color is changing again. So we just try to repeat it again. Color press 1. And this one is none. So what does So we got this one, and then we try to export it here, right? Whenever we done it, we just try to export into Google. So from here, we right click, and then so we put it into documents.
Excuse me, I think I get stuck. Can I ask you a question?
Yes.
When you make terrain correction, it was the filter, the mask displacement. What was the input of a terrain correction?
The terrain correction should be the final one. I mean, The one we have it here, that is the displacement
This is
final.
this is final, but this is
Yes.
virtual. There is, it's not no problem, right?
Yes. No problem with the Vitron. Yeah. Whenever we go it here, we are going to you got the same result. Thank you, David. So Emmanuel asked me about coherence, the concept of the interferogram. I mean, to be applied in measure of water level. Basically, that this is a very good question and very right one. Because why? Because that's what people are doing right now. Because at the moment, from space, we don't have the satellite which is able to use interferogram to measure the water level. But because why? Because you see the coherence in the water is terrible. It should be totally random. It should be close to zero. So because why? Because the first image and the second image usually they take a couple of days. Something like Sentinel-1 data is 6 days or 10 days. So basically that after 6 days or after 10 days, the water changing a lot. So we cannot retrieve anything from anything useful information from at the level of water. related to interferometric phase using the current satellite for interferometric phase analysis now. But in very next year, I mean in 2022 or 2029, because we're not sure about the launching day. The launching day after the mission, what we call, can I say, squad. I mean the squad, which one? The squad mission. The squad mission, they're using very soft wavelength, something like 8 millimeter wavelength. And how can I say, they're using 8 millimeter wavelength, and also they have something like I'm not sure, a tandem system. So basically that's the tandem system. It means they collect 2 images at the same time. To avoid correlation. So in this case, the phase of in this case, the interferometric phase of squash can be converted to level to surface to water surface to water level. That's what I know from the perspective of the SAR interferogram. Until now, we cannot do that, but in the very next year, 2020 and 2023, 2022 and 2023, we're not sure about when will the satellite will be launched, but using the system of the 8 millimeter and using the panel system, the squash is expected to be able to measure the water level using interferometric phase. You're welcome, Emmanuel.